Okay, so it's 4 o'clock now. Welcome everybody to a new seminar in our Landscapes Live seminar series. My name is Steffi Tefelder. I'm going to moderate today's seminar together with Philippe Stier and Pierre Waller. And our today's speaker is Ajay Limaye. And I'm going to introduce Ajay very briefly. Then I'll shortly explain how everything is going to work before I pass over to Ajay. So Ajay did a bachelor in geophysics at the University of California in Berkeley. And from there, he moved to Caltech for his PhD, working in the group of Mike Lamb. And after his PhD, he moved from California to Minnesota, where he did a postdoc for several years at the University of Minnesota and St. Anthony Ford's laboratory, working with Chris Paola. And after that, he did another, I think, shorter postdoc at Arizona State University before he was appointed an assistant professor at the University of Virginia since in 2019, where he is now leading the Landscape Evolution Group. And today, Ajay is going to talk about rivers. We have a slightly adjusted title. It's going to be Nature Doesn't Make Straight Lines, Interpreting River Forms Through Time. So we are very happy to have you here. And the way it works is that Ajay will talk for about 40 to 50 minutes. During that time, the chat is inactivated. And towards the end of the talk, we will activate the chat so you can ask questions or post comments. If you would like to ask a question, but you feel somehow uncomfortable to have your name put out there, because you're not really sure if your question might sound a bit if you're just a little bit shy, that's no problem. You can send your question also privately or like in the private chat to either Philippe, Pierre, or me, and we can read out the question without saying your name. Or the alternative is also to use your microphone. So at the bottom of the chat, you should be able to see a little hand. So you can click on that button, which raises your hand, and we can give you the permission to actually unmute yourself and ask your question directly. Yes, so with that, I'm going to hand over to Ajay, and I'm very much looking forward to your talk. Thank you very much for coming.
Thanks so much, Steffi, and thank you to the whole Landscapes Live team for making this possible for us to continue to connect as we kind of round the 1 year mark of having to be physically distant from one another. These are really valuable, so really appreciate that work. So today I'm going to talk about river forms and their tendency to deviate from the strictures of a straight line, how they evolve through time. And I'd like to acknowledge funders who've supported this work, the American Chemical Society and the National Science Foundation. Okay. Also, several collaborators have had important roles in contributing to this work. So those include Yuan Li and Jake Smith, 2 PhD students who are just getting started here at the University of Virginia, Eli Lazarus over at University of Southampton, and John Schwenk at Los Alamos National Lab. So to introduce the kind of themes that we're exploring here in the Landscape Evolution Group at Virginia, a lot of what we're interested in, and I know these are topics that are of interest to many in the room, are how rivers really give us a thread of connection through time. Obviously, rivers give us records of the past through the evidence they leave in the geologic record in the form of landscapes and sedimentary deposits. Vital in the present because they're hubs for life and natural resources. And then as we look to the future, and in particular thinking about sustainability and the stability of our infrastructure going forward, rivers also play a central role. So today's talk, I'm going to focus on 2 particularly widespread examples of fluvial forms, and we'll really focus on trying to place them in a temporal context. So the first form I'm going to talk about is meandering rivers. This is, of course, the most common type of river geometry that you probably see on the surface of the Earth. And we have lots of beautiful and familiar examples from a long history of scientific study. So one example will be the work in the lower Mississippi River Valley by Fisk, who made these very colorful maps that you can even find in Etsy products nowadays on the internet. And of course, in recent years, there's been this revolution in our ability to look at meandering rivers, thanks in large part to the long baseline, the Landsat data set, from which Sultan Sylvester made this beautiful movie a couple of years ago. So a key aspect of meandering rivers and these images that are so powerful to us is that very often we link meanders to migration of the channel. The idea in these images is really migration plays a central role in the form of this key landscape feature. Yet the role of migration over time is not always so obvious when we think about meandering river forms. And a classic example is the really deeply entrenched meanders of the Colorado Plateau region in the southwestern United States. So the San Juan River is one example of this case where, on the one hand, we have a very familiar feature, this meandering river that's flowing from right to left across this image, but it's in a very unfamiliar context. It's deeply embedded hundreds of meters into a bedrock canyon. That bedrock is made of resistant sandstone that would seem to prohibit the migration of the channel. And so this has long been kind of a conundrum of to geomorphologists going well back into the 19th century. And again, the central issue in this case has been timing. When did these meanders form? Did they form in kind of a previous alluvial state and then get burned into this bedrock landscape by uplift and erosion? Or are these features that were made kind of over time in this landscape? So we now know, with the benefit of many decades of hard work, that even in bedrock, meandering rivers can evolve their sinuosity over geologic timescales from thousands to tens of thousands or hundreds of thousands of years. Here's a nice example of bedrock meanders and what they've left behind from Kerry Johnson's work. So we're looking at a shaded relief map of LiDAR from a creek in the Coast Ranges of California, and we can see great evidence of evolving sinuosity, for example, in the form of this cutoff loop on the left, or the example of these stepped strath terraces on the right. So these types of observations and this growing awareness that sinuosity can evolve, even in settings like this, really opens up an interesting possibility, which is that if reverse sinuosity indeed does develop over time, that means it can keep track, or it can record factors in the environment that are transpiring as sinuosity grows. So it can record environmental forcing. Now, Colin Stark and colleagues seized on this opportunity in a paper about 10 years ago now, where they linked the sinuosity of river meanders across a large geographic region to different measures of climate, and for example, the kind of storminess that occurs in different catchments. And what they found was, in this case, a correlation between sinuosity and storminess. So this is a really exciting opportunity because, since meandering channels are so widespread, sinuosity can record environmental forcing. It's a very powerfully potential way to interpret recent landscape evolution. Now, I know this is a virtual trip to Europe, but I'd still like to tuck in a little bit of tourism along the way, since this is far afield for me. And so I'm going to stop by Park Güell in Barcelona, and perhaps some of you have been there and gotten to know this very colorful salamander who hangs out in this park. So I imagine that if you were to go up to the salamander and you placed your ear right up to his mouth and you listen very closely, you might hear the words of the architect Antoni Gaudí, of course, who designed so many famous buildings in Barcelona. And I found this quote, at least attributed to Gaudí, which is that there are no straight lines or sharp corners in nature. And he applied that to the architecture. All right, so how does this tie in to the talk? Well, it does seem that there is some truth to the statement. If we look to channels in particular, and if we try to find a straight channel in nature, it's very, very difficult to do. So one might imagine we might find a straight channel by looking at a channel that just formed, totally brand new in a landscape and hasn't had any time to migrate and develop its sinuosity. And one example of that could be a rill on a hill slope. So this is an example from a burned hill slope in the Rocky Mountains in the US, where we can see it's freshly denuded, and in that state, a new small rill has been carved into the landscape shown here on the right. And we can see, of course, that, as we'd expect, it's not totally straight. It's close to straight, but it still has this kind of residual wiggliness or sinuosity to it. So this is a local observation, but it poses an interesting consequence, which is that if natural channels are never really totally straight, that means that some sinuosity seems to form randomly, for example, from initial flow over an irregular surface. This poses a question then: to what degree is the sinuosity of channels that we observe a random feature? Now, in comparison to those examples like the Mississippi or the rapidly migrating rivers of the Amazon, in those cases, we know the river migrated a lot. But in many other cases, if we pick any one channel on Earth's surface, it can be ambiguous to determine whether sinuosity is kind of a random feature or whether it developed over time from progressive migration of the channel. One example of this kind of ambiguity was pointed out by Alan Howard in a paper in the book chapter in the mid-1990s, which is this, again in Colorado, this nice pleasant creek flowing through an alpine meadow, Fall Creek. And so we can see it's coming in from the left, it's meandering about the landscape, and then it goes off the right side of the image. So some things Alan noted about this particular example is that there are no obvious indicators of channel migration in this landscape. So of course, you don't see the channel migrating today if you were to look with year after year observations. And if you look around this landscape, you don't find things like scroll bars or terraces or other features that would give you a hint that there was active migration in the past. And so there's ambiguity about the role of kind of initial conditions and subsequent migration in the evolution of this channel sinuosity. All right, so to test the significance then of sinuosity, what we really need is a null hypothesis. We need a way to estimate kind of the background rate of sinuosity production that is kind of independent of change over time. To put it another way, we're going to ask how much sinuosity would we expect to form initially purely by random chance without any channel migration happening. Another theme I'm going to talk about in this talk is the second very widespread fluvial feature, which is the channel belt. So a channel belt is just the wider region that's shaped by any channel that migrates or shifts in some way, for example, by an avulsion across a landscape. So channel belts are probably most widely described for meandering rivers, as we talked about in the first few slides. So to see an example, this is the Missouri River in the US. The river trace channel is the trace of the channel is shown in yellow, and so it's going from left to right across this image. And then the channel belt is this wider zone that's outlined in white. And so within that channel belt, you can find lots of evidence for channel migration, things like especially scroll bars and abandoned channels, cutoff loops, and so forth. Now, even though they're probably less widely described, channel belts also occur for braided rivers. I picked one of the many beautiful examples from New Zealand here, the Rakaia River. And again, we can see a zone with an active channel. It's got multiple threads, but it's an active channel shown in yellow. And then there's a larger envelope of the channel belt shown here in blue. And we can tell that this is a zone that used to have channel activity. There are, for example, strands of abandoned channels, but it's now vegetated and it's long been abandoned. So channel belts also have significance beyond kind of the curiosity of geomorphology. So they're very key aquifers in many parts of the world, and they're also the building blocks of fluvial stratigraphic models, some of the classic ones, especially the Leader, Allen, and Bridge series from the 1970s. So these are really key features for reconstructing and interpreting past environments on the surface. So what can we do to actually understand how channel belt develops? Well, for meandering rivers, we have some tools to do this. In particular, there are a number of theoretical models, which I'll talk about a bit more, which we can use to run over time and kind of estimate how would a meandering river shift across the landscape over time. So a nice example is shown there in the lower left, where we can get an estimate of the width of the channel belt made by that meandering river. On the other hand, for braided rivers, we have fewer tools to really predict their long-term evolution and how they would build a larger aggregate feature like a channel belt. What we mostly have in that place are empirical relationships, for example, between the width of a channel belt and the depth of a channel that we observe today. And so these types of empiricisms are the most widely used tools to try to infer the subsurface architecture of channel belts. I do note one important exception to this, which is new work by Aaron Buffa and colleagues. I know many of you are probably here on the call today, which has made some progress in establishing quantitative relationships for channel migration. And it would be great to talk more about that as we get to the discussion. But the larger question of the development of channel belts still has some gaps. And I'm going to ask in this talk, can we develop a theoretical predictions for channel belt width, in particular, how it evolves from an initial condition to the forms that we see over time. Okay, so to frame the rest of the talk, I'm going to break it into these two parts, focusing on each of these common river features. And we'll look again at how these features, the kind of role of time in their evolution. So in part one, we'll ask the question, to what extent does the sinuosity of a meandering river owe to randomness in the initial channel path? And then in part two, we'll shift to channel belts, and we'll ask, how do channel belts specifically evolve for braided rivers? Okay, so let's go ahead and jump in with part one. Again, we're going to focus on the role, trying to quantify the role of randomness in the initial path in setting river sinuosity. So we're going to approach this problem using sinuosity as a statistical measure, which is probably the most common way to look at a river. And it's a very simple statistic. So we're just looking at, for any given river, we measure the distance along stream, shown in red. We divide it by the straight line distance from start to end, and we've got sinuosity. So for natural rivers, sinuosity tends to occur in a pretty constrained range. And so the geometric limit is 1, and sinuosity values can occur from that up to about 3. It's very rare to see sinuosity value greater than 3. So the specific hypothesis we're going to explore here is that the plausible range of this random initial sinuosity is limited. It's got some kind of finite bounds on it. And to return again to the example of these rills, we can see that they have sinuosity to them, but it seems to be limited. It's pretty constrained. They're almost straight, but not quite. So that leads us to consider, how might we model or estimate quantitatively the role of randomness in setting the planform geometry of a channel? Well, when you think about single thread channels and their geometry, there's a good chance that the first thing that comes to mind is an image like this. This is an example of one of the many models of river meandering that focuses on channel migration. It comes from the work of Frascati and Lanzoni. And you can see here over time, we start from an initial channel. The channel migrates. As it migrates, it grows these cutoff loops that get abandoned. And so we can see kind of a history of migration that's reported, leading to the final state of the channel shown here in red. So this is emblematic of this whole class of models that really focus on the migration process and its relationship to the planform development. So these models have had very important successes, so they can reproduce the skew, or kind of upstream pointing that's common in meander bends. They can reproduce the wavelength that common to meanders, and also different geometries of bend migration, for example, across or down a valley. But important thing to note about these models is they really weren't intended to ever model the initial condition of a channel, right? They're really set up to focus on the migration process. So if we want to think about the very widespread models. Okay, so to look for a way to model the role of randomness, we can actually set further back in time to the class of models that existed before we had these great and effective meander migration models. And so if we look at studies, particularly in the 1960s and 1970s, several investigators, starting with Leopold and Langbein, use statistical models to approximate the form of meanders. And they especially use random walks to try to treat this process. So the principle here is very simple. We start out at one point, this dot on the left. A random walk poses that we have to make some kind of decision about which direction to move, and then we take a step. When we get to the next point, we take another step in some other direction, and so on and so forth, to eventually build up the geometry of the channel. So in the kind of years after this idea was proposed, it was eventually realized that simple random walks are really not good descriptors of rivers. So Ferguson in a 1976 paper in particular pointed out that if you set each step to be totally random, so we set each theta direction to just follow a random disturbance, you end up with this kind of winding, self-intersecting path that looks something like this, shown in the lower left. So this kind of squiggle is evocative of the drunkard's walk, which is another kind of common nickname for a random walk. So we need something different from just this very simplest form of random walk. Now, what's missing is probably some description of inertia as a concept. So real channel flows don't kind of pop and change direction continuously, but they have some kind of spatial memory to the way they move across the landscape. And so we can model this behavior very simply by just making each step in this random walk dependent on one or more of the previous steps. And Ferguson in the same paper showed that a successful approach for doing this is to set a direction series where each step, theta I, depends on both the previous step and the step that came before it. And then we still add that original random disturbance. And so there's, again, two components to this kind of random walk. There's a spatial memory, and then there's a random disturbance, which is always kind of poking and trying to make the channel move in different directions. Now, there's no physics in this model. It's totally agnostic about the processes, but you could imagine that, for example, this random disturbance could represent irregularities just in the topography that a channel is establishing itself on. So this is because this model depends on the previous steps. It's also known as an autoregressive model, and it's second order because it depends on two previous steps. So this is commonly known as an AR2 model, and I'll refer to it as that in the next few slides. All right, so what does this model actually do? Let's see some of the output. So what we've done here is just taken a few realizations of the model, all generated with this very simple equation. And what Ferguson actually generated these. And so this is an example where we have 4 examples of modeled rivers, and one example of a real river is actually in the mix here. So we're going to take a quick pause in the Zoom, or we'll stay on Zoom, but we'll take a quick pause in the proceedings. And I'd love everybody to participate. So I'm going to ask which of these channels is real, 1, 2, 3, 4, or 5. So please submit your vote. As an answer, just drop an answer in the chat, and we'll just take a few seconds to do that. See if we can approach 50% turnout, which for America usually is pretty good. So Steffi, what are you seeing come across in terms of responses?
Yeah, I'm seeing lots of numbers coming in. Every number did come in several times. I think it's super hard to say if there's one number that came in more than others. If anything, I would say 2, but yeah.
Okay.
I'm not exactly sure.
Thanks very much. And I put Steffi on the spot. This is a very non-scientific approach, but I think the polling shows there's no clear favorite here. Or maybe if there is, it's 2. So let's see what the real river is. It turns out it's 1. This is a real river, the River Trent. Perhaps some of you have been there. So, this is obviously a very non-scientific approach. We're kind of judging realism by eye. But I think it does show, that there is certainly a possibility that this random model captures aspects of river geometry that are very common, that we have common experience with. So I'm going to argue that this is really the simplest model for a randomly generated river sinuosity that's consistent with natural river shapes. And so we're gonna run with it and see what it tells us. What does this model actually tell us about the possible range of a randomly generated sinuosity? So to explore this, we use a systematic parameter sweep across the different parameters in this AR2 model. So again, each direction in our random walk is going to depend on the previous step, the step before that, and then a random disturbance. So we have 3 separate parameters we need to go through: the weighting coefficient, B1 and B2, and then the magnitude of this disturbance, and then different realizations of it. So we used a systematic parameter suite with more than 1,000 simulations to determine the range of possible sinuosity values. So I've just pulled a few examples from this big stack of rivers, synthetic rivers on the bottom. So for example, we can see the effect of the parameter B1 if we fix B2 and the random disturbance sigma. We can see that as B1 is small, we have kind of low sinuosity, and then as B, and there are different behaviors that we could get into in the discussion if we look at the effect of these different parameters. But for now, we'll just leave it that we look through the different range of possibilities of sinuosity that you can develop with this model. So this is an example of synthesizing the results of many of those simulations and looking for average behaviors that account for different random series that we could feed into the model. So what we're looking at here is a plot of sinuosity, and it's a phase space where on one axis we have the parameter B2, the other axis we have the parameter B1, and then this is for one value of sigma, that third parameter here in our formula. So what do we see in this image? Well, one thing is we can see we see a lot of blue, and so that corresponds to very low sinuosity, somewhere in the range of 1 to 1.5 for basically all of these cases. We also see a big area of white where the model becomes unstable, and so specifically that means that the channel is kind of re-intersecting itself pretty frequently. And only kind of on the margins of the stable part of phase space do we see any sinuosity values that get anywhere near 2 or beyond. So for the most part, the stable kind of portion of phase space in this model gives us relatively low sinuosity values. And that holds if we look across the full range of model parameters. So here we're looking at the same range of B2 and B1, but we're cranking up the value of sigma, that random disturbance. And because that random disturbance is poking the channel and trying to get it to move in different directions, we can see a slight increase in sinuosity as we go to the right across this image. But again, sinuosity is pretty constrained and it's generally below 2. So we can see randomly generated sinuosity again, for the most part, does not exceed 2 in any stable portion of the phase space. And this holds for all reasonable parameter values that we can explore. Now, we could talk about where these parameter ranges come from, but the short answer is that this is essentially consistent with kind of the range of fitted parameters that you would find if you applied this to natural channels. So we're talking about changes in fluvial forms through time. So let's think about how this kind of random initial condition could interact with subsequent channel migration to explain kind of the composite form of a meandering channel. So what we're going to do is take just one example of a synthetic channel created with this initially random form, and we're going to evolve it using a very simple model for channel migration from Howard and Knudsen. This is meant just to evoke some of the general behaviors of channel migration models, even if it's relatively simple. So to keep track of the change in the channel over time, we'll use a non-dimensional framework. And so this lets us explore different lapse times, migration rates, and channel scales, kind of collapse them all into a consistent framework for looking at the evolution. So we're going to track dimensionless time as the channel evolves by migration. Skip the slide. Okay, so here again, we're starting with an initial condition at time equals 0 that is randomly formed. And we can see that as we'd expect, as the channel starts to migrate, we get smoothly varying meander bands develop with a nice consistent wavelength, and their amplitude increases over time. So that by the time we get to the right side of this plot, we've got a high sinuosity channel that has these nice even meander bands formed by migration. So the key thing to emphasize in this plot is that channel migration is a pathway then to start from a low sinuosity condition and get up above this threshold of 2. So again, 2 is kind of that critical number, which seems to be the cap for randomly generated sinuosity. So it means if we see a sinuosity value above 2, it very likely means the channel migrated. So let's compare these predictions to some data. So we compared to a global data set of rivers generated from satellite images. So we have more than 30,000 observations in this data set. From this histogram, again, you can see the typical range of sinuosity is somewhere from 1 to about 3. And we can see that if we plot our limit for that randomly generated sinuosity on here, we can see that it actually captures quite a lot of the distribution. And so at most 84% of these observations are at least consistent with a random sinuosity. Now, that doesn't mean that none of these rivers migrate, but it does suggest that randomness could certainly play a role in explaining their evolution. Now, if we separately look at just rivers that have documented migration, we can draw on a couple data sets that focus on this. So as many of you have seen, no doubt, there are these beautifully, very actively migrating rivers in the Andean foreland that move fast enough to be well documented. There's also a fairly large data set from the continental US. And so if we take those rivers and just plot their sinuosity, what we can see is that they commonly can punch above this ceiling of the limit for random river sinuosity and can get sinuosities in this range of 2 to 3 pretty commonly. So that lends some credence to the idea that river migration is actually this key process in getting rivers to that higher sinuosity. All right, so we'll wrap up this first part of the talk, where again, we were asking, what's the role of randomness in setting the initial path of the channel? What we found is that the simplest plausible model for randomness, an AR2 model, has a pretty strict limit for sinuosity. Doesn't really generate channels with sinuosity greater than 2. And so we can use this behavior to diagnose whether channels have migrated. Specifically, if sinuosity comes out greater than 2, there's a very good chance the channel migrated to establish that geometry. So we'll look at some implications of this finding. So one is interpreting environmental forcing from sinuosity. So if we're going to do things like link past climate or tectonics over time to the sinuosity of channels, we should really keep a null hypothesis in mind. And this offers actually quantitative framework for doing so. So we should consider randomness in particular as a potential source of sinuosity if we're looking at rivers that have sinuosities less than 2. Another implication is more direct on the ground for river restoration practitioners. So it's a common practice in river restoration to have to design the form of a channel that's being kind of reestablished in a landscape. And so this work would suggest that the sinuosity that's designed in any single thread channel, at least, should reflect regional patterns of channel migration. So if you're in a region where channels seem to move around quite a bit, it would be sensible to have a sinuosity up around 2. Whereas if it's a region where channel migration is not common, sinuosity would be probably more kind of geomorphically and ecologically appropriate if it were set in a range below 2. All right, so that wraps up part 1 of the talk. We'll take a quick water break and then we'll go into part 2. So we've been talking about meandering rivers. We've been talking about initial conditions of those rivers, how they might evolve from that state. In the second part of the talk, we're going to shift to braided rivers, and we're going to think about channel belts specifically that evolve over time. So we have a wealth of a rich tradition of experiments to draw on to inform us in understanding the evolution of channel belts by braided rivers. So a very common setup that goes all the way back to Friedkin in the 1940s is that you can set up, if you just set up a bed of sand and you just carve a channel through it and you route water through that, as long as you've got erodible material that can interact with that flow, eventually first you develop meanders and eventually it breaks into braiding and eventually a separated channel and channel belt. And so this is one of those just happy circumstances of laboratory science that with very simple conditions, we can get this beautifully interesting result. So this same flavor of setup has guided many subsequent studies of braided rivers. Here's an example from Moores at the University of Wyoming in the early 2000s with a very almost identical setup. Peter Ashmore, of course, has conducted many experiments in this vein. And then Walter Bertoldi and colleagues had this set of experiments specifically focused on the development of the channel belt by braided rivers that came out in 2009. So I'm going to talk a bit more about the study because it really identified some very interesting phenomena for channel belts. So we're starting with a laboratory case, which is admittedly very, very simple, right? We're removing a lot of the complications that one would see in a natural river. But I think this is a good place to start because even though the setup is very simple, we still lack ways to really fully predict the evolution of a channel in this context. All right, so going back to those Bertoldi et al. Experiments, a couple of the things that they noted that I think were quite interesting. First is that the channel belt width depends on discharge and bed slope. There was not a very, there's a lot of scatter in some of the data, but there did seem to be some relationships between these variables. And then perhaps most interestingly, the channel belts didn't widen indefinitely. So even though the material was all erodible and there's always flow, the channels seemed to only develop a channel belt that had this kind of finite width. And so this was described as a quasi-equilibrium state in this paper, which is very puzzling in some sense. So there's nothing constraining this channel from going all the way to the edge of the basin, and yet it didn't do that. So it's a bit of a mystery why that wouldn't occur. So there's several outstanding questions, based on these really interesting results. First are, if we really isolate the independent effects of discharge and bed slope, can we more precisely quantify what those relationships are to channel belt width? Second, how does a form like this actually develop over time from that initial straight channel to this fully ramified form? And then, as I said, why does the channel belt ever stop growing? What is the nature of this kind of quasi-equilibrium state that it seems to approach? So to explore this question, we're going to start from a hypothesis that this quasi-equilibrium is actually something that's predictable, and it's something that may arise just in general in this type of setup due to a decline in sediment transport capacity over time. So the thinking would be as the channel belt develops, eventually flow becomes shallower, and at some point it'll just be difficult to move sediment and cause continued morphologic change. So we can work through a heuristic argument to end up at these couple predictions that come out of this framework of a channel belt driven by sediment transport capacity. So the first prediction is the channel belt width should approach a constant value, and we can predict that using this dimensionless form of the channel belt width, where what we've done is re-express the kind of original form of the channel belt using gravity, grain size, and then importantly, discharge and bed slope. And so what this is saying is that we predict, if the hypothesis is true, we'd expect essentially a linear relationship between channel belt width and discharge, and also a linear relationship between channel belt width and slope. And so if we know all these things, we should be able to account for those effects in predicting the channel belt width. The second prediction that comes from this hypothesis is that the channel belt should grow following essentially a consistent evolutionary clock. So if we account for the discharge and the slope in particular, we should be able to precisely, more or less, be able to predict the kind of changes in the evolution of this channel belt over time. So that's codified again in a different form of the dimensions time here that's tuned to this problem, where again we use time times gravity and grain size to raise to the power 2. And again, we have discharge and slope coming into the equation. All right, so to test this framework, I conducted a new set of experiments at St. Anthony Falls Lab on the Mississippi River at University of Minnesota. And I did this in a large-scale braided river experiment, really, standing on the shoulders of these many experiments by Peter Ashmore and Bertoldi and colleagues in previous years. So the setup we're looking at here, we're looking at a cross-section of a basin, and it's very long. That's one aspect to emphasize. So it's 37 meters from the inlet to the outlet. And within that big area, we just have a big pile of sand. And the sand is sculpted to a consistent slope so that we can vary slope as an independent variable in this experiment. On top of that, we just have water and sediment coming in at the upstream end. They're moving across the surface, and then they're just hitting kind of a synthetic ocean at the end. So a very simple setup that we just are going to monitor over time using time series topography and images. This is an overhead or bird's eye view of what that setup looks like. So again, following on previous experiments, we have a narrow, as straight as we can make it, channel all the way through this basin. And so we can see there's a lot of distance initially between the channel and the walls of the basin. So a couple of other things I'll note about the setup is that we really focused on collecting high frequency topography data as a way to characterize the evolution of this channel belt. So this is important because it allows us to map the channel belt pretty quickly and objectively, just looking at using changes in topography over time. Now, one might reasonably ask, why go through all the trouble to move all the sand to do an experiment at this very large scale, many tens of meters long? So there are the main reason is that it allows us to minimize the boundary effects within this basin. So the effects of the upstream, the downstream boundary, and then also the effects of these channel walls. So for the most part, we want to look at the evolution of the channel to channel belt, keeping these boundary effects at bay as much as we can. Another thing to keep in mind is that this long baseline gives us the opportunity to average over a lot of local variation in the channel, look at kind of system properties. All right, so our old friend the salamander is going to chime in right here and say, hey, wait a minute, there are no straight lines in nature. So why are you using this initially straight channel, which doesn't seem very naturalistic at all? And I'd say the salamander is making a very good point here. The point is well taken. But I think understanding how the straight channel evolves is a very good place to start, because we need to kind of ground our knowledge in what's come before, and hopefully this is kind of a simple point to start to build out into more complicated scenarios. So this is the evolution of one of those experiments. We're looking at a perspective view from downstream to upstream in this big basin. So we can see flow coming towards us, and we can see developing braided channel belts over time. I'll let that movie play a couple more times here. We start with that straight channel, very quickly develops meandering and braiding. And then over time, we can see parts of the braid plane actually get abandoned, making kind of a distinct, a larger channel belt than channel itself. So this type of setup is old hat. It's been certainly treated and characterized very well in previous experiments. And so what I want to emphasize is the really new part of this analysis is that we have topography data to go along with this evolution. So we can look at how the channel belt evolves from the very early stages of alternate bar formation all the way through to braiding and then the channel belt itself. So now we're looking at the same image sequence in the upper left, but now we can look at the evolution of the topography over time. So I've shown that in the map here on the bottom. What we're looking at is kind of a map of topography across the entire length of the basin. It's a little bit distorted just so we can see what's going on here. And we're looking at elevation change. You can get the scale there on the right. So areas that are red are grading, and areas that are blue are eroding, and then areas that aren't changing at all are shown in white. So what we can see here is the growth of an envelope of the channel belt. And we can see that it's very irregular, right? There's kind of this waviness to it that starts right from the beginning of the experiment. But interestingly, if we average and take the mean width of this form over time, we have a very smooth evolution. So starting from the initial state, the channel width evolves systematically. And just as Bertoldi and colleagues noted, it seems to approach this kind of quasi-equilibrium, or it's almost hitting an asymptote here at this channel belt width. So this data, then we've resolved this trajectory from our initially straight channel to a fully ramified channel belt. And we'll try to understand that using the different experiments. So that was one set, that was one run of the experiment. And then we can look at how the channel belt grew across these other runs that varied discharge and bed slope. And then also sampled all of the growth of the channel belt across time. Now, if we take all these different observations and we port them into this dimensionless framework, then we end up with the following. So we're going to plot the mean width of the channel belt in dimensionless form against the dimensionless time. And so now we see why we go through the trouble of porting everything into this framework, which is that in dimensionless terms, all the channel belts evolve in essentially the same way, even though to the eye, they can look quite a bit different between these experiments. So they all start at a relatively low dimensionless channel belt width. They go through this growth phase that all started about the same time. They seem to grow at the same rate, and then they all more or less roll over in their growth rate, perhaps with one exception. Also see this distinct growth phase actually corresponds to the onset and evolution of braiding. And so quantitatively, we can see that the dimensionless channel belt width grows with the log of dimensionless time within this window. Another thing we can do is try to put this together with previous observations. So if we take the data for the final state of channel belts from Bertoldi and colleagues and put them in this framework, we can see that more or less they plot, in a reasonable or a consistent part of phase space. So these mature or quasi-equilibrium channel belts all develop at these dimensionless times that are greater than 10 to the 3. And got magnitudes that are all in this range, somewhere from 8 to 12 or so. So they do plot a bit higher on the plot, but I think for this type of work, it's pretty close. So it does seem that kind of the results here are consistent with previous experiments. So that leaves one more question here, which is what accounts for this very mysterious decline in the widening rate? It's kind of quasi-equilibrium behavior. So to understand this, again, our hypothesis here is that it's a decline in sediment transport capacity that's behind this. So for anyone working in sediment transport, of course, the first number that you go to is the Shields number. If you're not familiar with it, it's just a way to represent shear stress in a dimensionless form. So it's got a very simple construction. We use the flow depth, the slope, R, which accounts for the relative densities of sediment and water, and then the sediment grain size. So how can we go about estimating shield stress in these experiments? Well, it's a very big scale, and we don't have direct measurements of flow depth. So what I did was use estimates of flow depth from the topography data. And then bed slope, of course, we can directly constrain and use that as an approximator for the water surface slope. So if we use that together, then essentially every time at which we have a topography observation, we can estimate what the Shields number was in that time. And so changes in the Shields number can tell us about the sediment transport state. All right, so what does this show? Well, if we put all of the runs together and we plot this estimated Shields number against dimensionless time, we can see, again, some consistent trends. So all of these cases start at Shields number well above critical, so well above the threshold of motion. And over time, they gradually decline. So 3 of the experiments actually got very close to that, near that threshold of motion value, as we can see here with the dashed lines of the plot. And the only run that didn't get to that kind of near threshold state was this run 3, which was stopped early due to interaction. The channel actually started to bump into the walls. So I think in some, these observations suggest that indeed these channels do decline to the state where they're just above threshold. And that explains why the morphodynamics essentially slows down to the point where it appears to be at a quasi-equilibrium. Now, it doesn't stop altogether. There's still slow change happening, but it's much slower than what's happening at the beginning of these experiments. So we've been in the laboratory entirely for this section on channel belts, so we can ask, how does this relate to the to real rivers in nature? And we've just taken some very beginning steps at trying to port some of these lessons from the lab out to natural cases. So this is a database that compiled of channel belts for natural braided rivers. So these are often in high latitude places like Canada, Alaska, Iceland, but also well-known braided rivers like the Brahmaputra. And so these rivers are useful because they span, for this exercise, because they span a wide range of discharges, of valley slopes, and of grain sizes of the sediment. And so we can see whether systematically the channel belt widths that are observed here actually conform to the dimensionless framework we've developed. And what, interestingly, they seem to diverge in important ways. So the natural channel belts don't systematically depend on slope or grain size, but they do depend, as you probably expect, on discharge. And so if we can see that, for example, if we just plot the mean in real world terms now, the mean width of the channel belt in meters against the discharge, and we put all the natural cases shown here on the right, and then all the experiment cases, we put them on the same plot. You can see this interesting behavior that across more than 8 orders of magnitude in discharge, they all kind of follow this consistent scaling, more or less, with channel belt width going with discharge to just over a half, which is kind of similar scaling that you would see, for example, between the thread of an individual river and discharge. So what we see overall is that the effective discharge on channel belt width is weaker than we observed in the experiments, because the experiments had a linear relationship between width and discharge. So this is an interesting topic for digging in further, and happy to talk about that more as we get to the discussion. All right, so to wrap up this part 2, we were looking at how braided channel belts evolve over time. using this kind of classic experimental setup that starts from a straight channel. So we found that within this case, we can actually use a dimensionless framework to reconcile the independent effects of discharge, the bed slope, and time on the growth of the channel belt. And so this framework, albeit for a simple case, provides an important reference point for interpreting channel belts because we can at least put some numbers on it. So I think the main implications for this type of analysis are for interpreting, or significant implications for interpreting the stratigraphic record. And I think that if there's one take-home point I want from this part 2 is that time is a key ingredient for channel belt dimensions. So I think for braided rivers, sometimes it's kind of thought that the channel and the channel belt are essentially the same thing. But I think the natural observations and what we're seeing in the laboratory suggests that actually we should think of them as kind of distinct entities. So the channel belts can certainly be wider than the channels that form them. Oop. Well, that's strange. Can you hear me on your end?
Yes, we can still hear you and see the emergency alert.
Yeah, so this is just, don't be alarmed. This is a routine test. I can hear some other things going off. So in any case, I'll see if I can get this off the screen. That's very strange.
Otherwise, maybe you unshare and share again, because we can still see the alert.
That. Well, that's a first. Okay, I got it. So let me reshare here. Yep, okay, so again, we were saying that thank you, JP. So time is a key ingredient for channel belt dimensions. So in particular for braided rivers, if the channel belt itself is wider than the channel, then that means that when we're interpreting channel belts in the rock record, should be mindful of that. Because if we just take the width of the channel belt, the width of the channel in all cases, that would lead to an overestimate of paleo discharge. And so I think that thinking could also inform alluvial stratigraphic models, such as the one shown here on the right. Okay, so I'll wrap up there. We made it to the end. So the big picture across, I think, these two examples is that to interpret fluvial forms, we can make a lot of headway by considering a continuum of geometries between initial forms and those that evolve over time. And so by being mindful of these kind of distinctions, we can make some progress across a lot of different applications. So of course, interpreting river dynamics in the past, as many of you do in your own work, restoring rivers in the present, and then also forecasting landscape evolution in the future. So I'll leave it there, and looking forward to this discussion. So thank you, everyone, for tuning in.
Yeah, thank you very much for this very nice and clear talk. We have activated the chat again. So yeah, I guess Ajay is happy to have questions and comments. And again, you can also raise your hand to ask questions, and we can allow you to unmute your microphone. The first comment in the chat is actually that somebody did the statistics on your question, on your poll.
Oh, fabulous.
And indeed, number 2 was voted 22 times. So at least I did my job somewhat correct. Number 1, which was the correct answer, I think, was just 7 times.
Very interesting. Well, thanks for digging in on the stats.
Yeah, I think, Ajay, you could also see the chat if you go to the bottom of the screen. Yeah, you should be able to activate it. Great. So I'm going to read out the first question, but then for the rest, I'm going to co-moderate with Philippe and Pierre. So the first question is from Wolfgang. He says, great talk. Can higher sinuosities in model channels be obtained by higher autoregressive models, higher order autoregressive models?
Thank you, Wolfgang, for the question. It is possible that a higher order autoregressive model could be applied to this problem. To my knowledge, it hasn't been done in the past. So the kind of history of or evolution of thought on this was Langbein and Leopold kind of proposed this random walk. Subsequent authors saw, well, totally random walk doesn't work, so let's add a first order dependent on first order autoregression to it. those cases turn out don't work too well either, because they have too much high frequency noise to them if you look into the statistics of the power spectrum. And so that's how we arrived kind of historically at the second order autoregressive dependence. Now, if you actually we went through and fit autoregressive models to natural channels, and they do consistently return significant regression coefficients for second order fits. So I'm not sure that you certainly could explore that structure, but of course it does come at the cost of a more complicated model. So that's an interesting question, I think, especially for statisticians to mull over.
Okay, so while people are still typing up the question, I actually used the time to ask a question myself, and it's about the second part of your talk, the braided channels. And well, I acknowledge that my question is about something you haven't really looked at in particular, but in your experiments, you particularly looked at settings where the rivers do not touch any walls, where you don't have any boundaries. So what do you think if there were any boundaries? If you were in a valley and you have valley walls, do you think the quasi-equilibrium width will be smaller or narrower, or will it just take longer to reach the quasi-equilibrium channel belt width?
I think both cases could certainly be true. So it'll be constrained. If the walls were there, it obviously can't get as wide. And then there's of course the possibility that it's going to try to break out of the walls. So especially the experiments that Aaron led, and that I know you've looked at that data as well, certainly give credence to the idea that the channel belt could widen significantly as erosion in kind of confined reaches moves forward in time. So then I think, one of the key questions then is kind of like, how long are the conditions relatively stable? As we start to think about valley widening and erosion, we're getting to even longer timescales. And so thinking about things like changing discharge, potentially changing grain size could start to become important. So I think to the larger point, yes, absolutely. I think confinement could play an important role. It certainly plays an important role in many cases in nature. So this would just be kind of the simplest starting point to start to interpret cases like that.
Yeah, thanks a lot.
So we have a question by Ben Everett on single thread streams. Do you measure sinuosity by mid-channel or by tile wag? And will this make a difference in assessment of meander growth?
Yeah, so I mentioned sinuosity being a very simple statistic, but of course anything in its application can have many important decision points. And so that is one of the important decision points in calculating sinuosity. What are we actually tracing? And so we could pick any number of things, like either of the channel banks, which of course aren't always the same distance apart because channel width can change. And then another option is, are we going to follow the Thelweg or the deepest part of the channel as opposed to just the midpoint of the channel? So I used the latter because that was the approach taken in the source data set. So the source data set was largely based on Landsat images. And so in that case, they're taking an image mask and narrowing it down in such a way that you're basically getting the midpoint of the channel without reference to any of the bed topography. So that could be interesting to explore that relationship. I think it's kind of a deeper analysis than we've done so far.
So there's a next question by Jintong Quinn, who is thanking you for the inspiring talk, and is asking, how do you decide the ranges of B1 and B2 for your space investigation of the AR2 model?
Yes, that's a very important point. So that the parameter ranges were relatively restricted, kind of this range of small numbers around 0. And so some of that has been determined previously in analyses of this autoregressive model, that you have kind of a limited portion of stable phase space. And so that said, so if you look to, if you take the same step length in this model, but you crank up B1 or B2, you end up with unstable planforms. So on the one hand, this could say, well, then it seems like this model is a little too sensitive and maybe it doesn't apply to nature. But what we found in other analyses is if you actually fit the autoregression coefficients to natural channels, they also tend to come out in this range, in similar ranges. So I'm sure one could go further on the kind of root statistical explanations for exactly why it's those values, but I think a short answer is it seems to work. So,
Okay, there's another question by Alex Whittaker, who was kind of asking a follow-up question to what I've been asking before. What do models experiments suggest about whether stability, for example, channel belt width, can be achieved when sediment flux or discharge vary? Does this depend on the timescale of Q or discharge variation compared to the timescales taken to reach equilibrium without this variation?
yeah, let me just look at the text real quick to make sure I caught everything.
Sorry.
That's it. A rich question. Yeah, so if sediment flux, so one of the other I emphasize the kind of geometric simplicity of these experiments, but another important point is that discharge was constant and sediment flux fed to the top of the channel were constant. Base level was also constant. Grain size of the sediment, all these things were fixed. And of course, are things that could vary in nature. So I think, I think you're on a good track there, Alex, in thinking about timescales of change. So, one way to think about the discharge in these experiments is that that fixed discharge could represent, a flood peak that recurs on a kind of consistent interval, in the same way that maybe the sediment flux could be thought of as a representative value. But those are nothing, at this point, they are mostly kind of informed prognostications, and could probably use deeper further work to look at those subtleties. There are some things though that for example, with discharge, we know that the big discharges are going to dominate the large scale form of the channel, and that smaller discharges are going to occupy a smaller footprint in the same braided channel system. So we do have some reason to think that using kind of a representative value, it's kind of a larger discharge, could have some explanatory power, even if a natural channel does go through cycles of high and low discharges we would expect on any number of timescales.
Chris Thomas is asking whether he can email directly you to ask a long question. So probably the answer is yes. And I remind to everyone that the video of Ajay's talk will be on the website tonight or tomorrow. So if you want to re-watch it. For the PowerPoint, I don't know if Ajay, you will share it or not, because this is a question that someone is asking.
Yeah, I'd be happy to follow up with anyone over email. I didn't put it in a slide, so I don't know the most efficient way to do it, but I'll drop it in the chat for now if anyone wants it.
Okay, great. Ajay, I have a question. You use in the experiments only 2 values for slope and discharge.
Yeah.
And in a small range. Have you tried to use higher values or a larger range of values?
So yeah, so there were these 2 values. So this points to one of the big trade-offs of going big. There's a lot of beauty, there's a lot of fun to doing a very big experiment, but what you gain in fun, you pay for in inertia. So just setting up one of these experiments took weeks. And to get to that highest value, so basically that highest slope value was chosen. We used all the sand that was available. It's 100 tons of sand in that basin to reshape to that 2% slope. And so basically just ran out of sand to go higher. There are other setups. So, there are other, I believe that the experiments used by Peter Ashmore actually have an adjustable bed slope. And so that would be a type of framework that could be better poised. I don't know what the maximum is, but could be better poised to kind of push those limits. So a lot of it, I think, has to do with kind of within the confines of a study at this scale. It kind of required being systematic or kind of confined in that discharge and slope range. Where we really could explore parameter space in a lot of detail was the time sampling, and I think that's really the unique aspect of these data.
And just to follow up on that, do you use a cohesive material or do you use a non-cohesive one?
This was all non-cohesive, kind of following, inspired by previous studies. But I think cohesion certainly can play a big role in the evolution of these channel belts. So particularly, seeing that scaling for the natural channel belts, that they don't scale linearly with discharge, but are closer to 0.5, to me suggests that cohesion probably plays a big role in these systems as well. So because cohesion is difficult to, it's a topic of active research in floodplains, but it's one that's going to take some time to tease out with this problem, I think. to me, I think, Alison Pfeiffer, who gave a talk in the series last week, I believe, is doing lots of interesting work on kind of relationships between discharge and thresholds and stress in channels. And I think there's potential for cross-pollination there to think about the effects beyond the channel itself.
Thank you.
There's another question by Steven Dijkstra asking, were your experiments done with a steady discharge, and how would unsteady flow affect the sinuosity and belt width in your models?
So yeah, it was a fixed discharge in any individual run. So we just had 2 different values for those braided channel cases. So the wavelength, we did look systematically at the wavelength of the initial meanders that formed, and I will have to go back and look, but at the exact relationship, but I'd be happy to follow up on that. But it is an interesting question. So there are these alternate bars that develop early in the experiment that drive these meanders, and those do can evolve in a systematic way that is treated in detail in that JGR paper as well, if you want to dig into it.
Okay, and just now another question came in from François Metra. You showed shield stress values of your experiments. Is it an average over the entire flume? What about local values and their evolution?
It is. So I believe it's a median value, because in braided rivers, notoriously, there's a huge, there's a wide and interesting distribution of things like flow depth and local bed slope. And so, the approach in this case is to gain as much as we can by looking at a big cloud of data and pulling kind of mean or median values out of it. But certainly there are local variations in shear stress. And we could see that, for example, in the time evolution of the topographic change. It probably went quickly in the movie, but there were kind of hotspots of change that had some coherence to them and moved. And that indicates that, certainly shear stress is not uniform, but did have important local variations. So that's something we're looking to follow up on pretty soon here.
Okay, it looks like there are no more questions in the chat, unless somebody posts a question right now. If not, I would like to thank you very much again for this really nice talk. And yeah, thanks everybody for joining in. And we hope to see many of you next week. Next week we have Roman DiBiase, and the week after we have Simon Mudd. And then we go into a little break during EGU and Eastern and come back with another block seminar in the summer, early summer. And I think for the summer block, there's still a couple of open time slots. So if you want to suggest any speakers, please send us an email. You can find the email address on our website. Yeah, thank you very much.
Thank you, everyone.
And bye-bye.